So it's my pleasure here to talk about our GTM project, and I thank the organizer for inviting me. And I believe that after the previous two talks, now the audience should be quite aware of what FS-8 will be, right? Okay, so I will talk about this gamma ray transient monitor on board this FS-8B. And I'm Hsiang-Kuang Chang from Taiwan University, and Zhixun Lin from Academia Sinica Institute of Physics, and Cao Zezhi from also NTHU and Department of Power Engineering. Zhixun Lin and Zezhi Cao, they are actually the real key persons of this project. Zhixun is taking care of all the real electronics, and Zezhi is taking care of mechanical structure of this payload. All right, so GTM, as you know, it's already selected to fly on FS-8B as a secondary payload, and the launch schedule is in 2024. So in this talk, I will briefly talk about science goal and our instrument design and current status. And as you know, the science goal, I can just explain the science goal in one sentence, but later I have more material. So that our goal is to monitor, mainly to monitor GRB, that is gamma ray bursts. And also, if we have some other bright gamma ray transients, then our GTM will also be able to detect that. For example, some burst from magneta or gamma rays from solar flares. And maybe Alfred Chen will be most interested is the TGF. If TGF is very bright, then it's possible GTM can also detect that. But according to our previous study, that TGF must be very bright so that we can detect that. So the chance may not be that high. And also TGF may have some beaming issue. So it may not be easy. But anyway, so in the following, I will go through science goal and instrument design and current status. So GRB, this picture is taken from these authors, and this is just an illustration of some transient event in the sky, not necessarily GRB, but GRB is very similar to this. We sometimes with our gamma ray detector, we detect a very short transient event from a certain direction of the sky, and it disappears within seconds, or sometimes longer and sometimes shorter. And now it's roughly our all the gamma rays satellites can roughly speaking detect 1 GRB per day. So since the discovery of GRB, it has been a long-standing astrophysical issue to understand what's the origin. So at the beginning, I think I will use this one page to show you the basic properties of GRB. The top left panel, the top here is one example of the light curve. This is so-called long GRB, the duration. The duration is several tenths of seconds. And this is light curve. You can see there are many peaks. And each GRB actually has quite different light curve, maybe a single broad peak or multiple peaks and so on. So the top right panel show you the GRBs if we plot them in the diagram of duration and hardness, spectral hardness, then we can see there are two populations. So in earlier days, simply based on duration, people have already realized that there are probably two different GRBs. One is longer one, and another one is shorter one. And of course, there are some overlaps in duration. So if we plot it in this 2D diagram, then the separation becomes better, but still we can still see there's overlap region here. But roughly speaking, we can see this is so-called short GRB, and this is long GRB. And also their distribution in the sky, according to, based on different brightness. In this business, we say fluence, that is integrated, time-integrated flux. Here, different color, this panel here, different color means a different fluence. But anyway, you can see it's basically all isotropic. Bright ones or dim ones, they are all isotropic in the sky. And the lower right panel here, this is taken from a Fermi GBM GRB catalog. Different color means short and long. So for short GRBs, they are also isotropic. For long ones, the same, they are isotropic. Okay, so it's difficult to understand the origin of these GRBs. They look like there are two populations. So until, the struggle, the effort to understand what GRBs are took huge progress in 1997, I think, because of the discovery or detection of afterglows and some host galaxies. Here I put two examples. Maybe this is the first example of afterglow. And you see this is X-ray image here. This GRB, 1902-28, astronomers also observed, in addition to the transient in gamma ray band. In X-ray bands, one also see a bright source and then which becomes dimmer. So that is also kind of X-ray transient thing. But afterglow, the time scale of the afterglow, the variation of afterglow is much longer than the GRB in gamma ray band. So here we call it afterglow. And you can see the same source. Also, in optical band, afterglow is also detected. So you see there's an optical source, and then later it gets dimmer. So from these afterglow observations, then astronomers can gain much more information about the possible physical environment of the source. And also, another example here, this GRB was quite bright in optical band, and it was found to be in a certain galaxy. Okay, so this is host galaxy of GRB, and later on there are more and more afterglows found, and more host galaxy found. So from all these evidences, then astrophysics are able to construct models which make some sense. All right. So roughly speaking, now in the mainstream market, GRBs, we divide roughly GRBs into long and short. And based on those studies on the afterglow and host galaxies, and also the prompt emission, the gamma ray itself, then most people believe long GRBs are hypernova events. That is, very massive star collapse and explode at the end of the evolution. But this is very massive star. So in this process, there are some details, but basically a jet will be produced. And in the jet, there are some shocks. Which happens first is the one called internal shock, which produce gamma ray, and later there are some external shocks which produce X-ray and optical and even radio waves. So this kind of model is called collapse model, and very often when it is possible to determine the redshift from afterglow and host galaxy, then we found that GRBs are at high redshift, quite high redshift. So they may have something to do with the first star formed in the universe. Okay, and then for short GRBs, people believe they are mergers of two compact objects, like a neutron star and neutron star, or a neutron star and a black hole. And for neutron star and neutron star merger, then it is a kilonova event. And similar to the long one, when the merger happened, there is a jet ejected from the central engine, and then in the jet, similar situations happens like in the long one. So one also see gamma ray and some afterglows in other bands. And short GRBs are, okay, they are mergers, and this kind of merger is expected to emit also gravitational waves, which should be detectable by current instruments. And indeed, in 2017, there was an event which is a short GRB and at the same time detected by LIGO. So it's also a gravitational wave event. And this is a very, very great identification that is from electromagnetic observation and gravitational wave observation, very independent observation. Then people come to the same conclusion. From that gravitational events, people also infer that comes from the merger of two neutron stars. And on the electromagnetic side, for a short GRB, it has long been suggested they should be neutron star mergers. So this event provides very, very strong supporting evidence to this kind of models. So very good. Then, what's our problem? What's our problem? So the story I just tried to explain to you actually has many details to be fixed yet. For example, are they really true, the collapse model? So the details of the acceleration of particles in the jets, whether it's like what the model describes, that's still an issue. So we need to have more examples to examine those models to check their emission mechanisms. And also if GRBs, long GRBs are at high redshift, can they provide some help for cosmological study? And can they provide some hint for us to understand structure formation in the universe? Okay, and for gravitational wave events, so far, the 2017 event is the only one event which is detected in both electromagnetic wave and gravitational wave. But you know, we have a lot of short GRBs. We also have a lot of gravitational wave events which are believed to be caused by merger of neutron stars. But so far, we have only one example. So is there anything wrong? Then we may need to have more examples, more observations to check all the theories. Okay, so among all this, the first star issue I mentioned maybe is quite interesting one. Here, this picture here, I guess many people have seen this picture in different occasions. Anyway, from the Big Bang here, and when the universe cools down, and electrons and protons, they combine into neutral hydrogen, and our universe enter a so-called dark age. And then later, if the temperature further cools down, and some material, they start to form structures, So then we may have first star, and those stars provide light to ionize the material again. So we have the later evolution of structures in our universe. So roughly speaking, now the first star, based on many different models, People believe it happened at about 400 million years after Big Bang. Okay, then whether the whole story is true, maybe we can use GRB to check. I mean, to find, let's try to find first GRB, which means first black hole, which means first star, right? So right now, the record keeper now is this one, GRB 090423. The redshift is 8.2, so it is about 630 million years after Big Bang. So it's not yet to this number here, 400 million. So if later we can push the limit to this number, well, that's good. But if somehow we push the number beyond this number or smaller than this 400 million years, that's even better. That will cast some strong challenge to the structure formation theory in our universe. So more GRB monitors may help to catch this kind of very high redshift GRBs, because they could be missed if we do not have good enough sky coverage, deep enough sky coverage. Okay, so what I were talking, the understanding what we have actually is based on observations, heavily based on observations of ether growth and also detection of host galaxies. And to have good observation of ether growth, to have very good detection of host galaxies, we need to have sky coverage, good sky coverage, and we also need to have good localization capability. So more GRB monitors are desired to enhance sky coverage and provide better localization. And in this regard, small instruments actually can do that, can help. So that comes to our project, GTM. GTM, this is Formosat 8, and GTM will be put on, we call it minus y side and positive y side here, the small one here. The dimension for Formosat 8 roughly 1 meter on one side. And this is small one, 10 centimeter roughly. And for one module, we have two modules on both sides, okay? And for one module, GTM, it will look like this. We have 4 detectors. This is 1, 2, on the other side, 3, and on bottom, 4. Each detector faces different directions. Therefore, if there is a GRB happening in some direction, so these detectors will have different flux. So from the difference in the flux of each detectors, then we are able to determine the direction of GRB. So that's the basic idea of GTM, okay? And for each module, this is one module. For each module, as I said, there are 4 detectors. And from this figure, you can see we open this one, and this is one detector, and there's a cable connect to a readout board, and 4 detectors, they are all connected to the readout board. And for each detector, it's like this one. And if you explore the image here, the detector, the sensor unit is composed of a scintillator array, and we choose to use GAGG as the material. And the scintillator here is attached to SIPM, which will convert the scintillation light into electric signals to our readout electric circuit here. So this is a PCB. Okay, basically it's just like this. And the dimension here, because the whole thing is just 10 centimeter, and 8 centimeter. So the detector itself is roughly 5 centimeter and 8 millimeter thick. So this is the dimension. So from here, then we actually performed quite a lot of simulations to see how well we can detect GRB. For example, this figure here shows the effective area of one piece of our sensor, and this is energy as a function of energy. So for the sensor, gamma ray comes in, it can be absorbed. So this is the red line, absorb, then we will have a signal. They can also scatter. They can also scatter. We also have signal. They can even make pairs, but the chance is lower. So you see this curve here, which is lower. And we will collect all these different kind of signals. So the blue one is the sum of all the signals. And you can see at roughly 100 kV, it's close to 23 centimeters square. So the efficiency is quite high. And if we consider the effective area larger than, say, 5 centimeters, so that's about 20% efficiency. So the sensible energy range will be from 15 kV to roughly 2 MeV. Okay. And also, from the simulation of on-orbit background, then we can compare the background value and the typical, GRB count rate. Then we can determine down to how dim a DRB can this GTM detect. So our result is like this. This figure is taken from Fermi GBM 10-year GRB fluence distribution. So from our simulation, then we realize that our GTM can detect, can have a 3 or 4 or 5 sigma detection down to this brightness for long GRB. This is short one, this is long one. And for long GRB is like this. And according to this number here is 1200, and this is 10 years. So per year is 120 long GRB. Our GTM can detect per year, according to this information, per year, 120 GRB. For GRB brighter than this, then we are able to detect that. But our duty cycle is roughly only 1/3, because basically this GTM is the secondary payload, and it will mainly operate in the night side. Yeah. So we should multiply 120 by a factor of 1/3. So we can expect that GTM will detect about 40 GRBs per year. But this number is also quite good enough. It's roughly 1 per week. Okay, so that's I think that's good enough. And in the following, I will show you some current status. We have already finished the design of the readout system. And here I won't go into the details, but as you can see, we have 2 modules. So this is a master module, and we have another slave module. They are basically identical. And for each module, we have 4 sensors. And each sensor, we have 16 channels. So we have a front-end ASIC to take care of 32 channels. So we have 2 front-end ASIC. And the signal will go to one FPGA, and there are some connections to the satellite bus. Okay. And we have not only finished the design here, but also we have produced a prototype of the readout board in the master module. So you can see it's this one. Okay. And for the sensor, we have some prototype. This is the PCB and a flex cable. And on top of this PCB, we have some SIPM on top of that. So you can see these are SIPM. And on top of the SIPM, we put scintillators. And these are GAGG. So we put upside down, so you can see in the lower right panel, these are GAGG. And then below the GAGG, is SIPM, and below SIPM is this PCB with this flex cable. Okay, and GAGG is wrapped on the 5 side, the side and the bottom here, that is the top here, with a very thin aluminum. So you can see it's a silver color here. Okay, so this is one sensor unit. And okay, this is important. This is an interface we chose to be the interface between GTM module and testing computer. And for the module, this one, we have already produced a 3D printed model of our GTM module. So you can see one detector unit here, one detector unit here. This is only a box, okay? And for each one, we open this one, so you can see this is the sensor unit, the PCB of the sensor unit. So below this one, there's a SIPM, and below that, scintillator array, and there's a box encloses that. Okay, so this is the mechanical structure. So, and also, as I mentioned, that we will use a different flux level of different detectors to determine the direction of the GRB. So here I show you the effective area of each detector in different directions in the sky. For example, this one, then the effective area is of course direction dependent. Therefore, this one, the top one, this one, the effective area distribution is like this, the lower left one. Here, the color bar means effective area, and I believe you cannot read the numbers, neither do I, but anyway, the blue ones is close to 25. The blue ones, the bluer, the larger effective area. So you can see this detector will basically sensitive to this part of the sky. And then this detector will be sensitive to this part, and this one on the side one will be this part, and the bottom one will be this one. Therefore, if a GRB happens in a certain direction, then these 8 detectors, of course, will have different flux. And so from all these flux, then we can determine the direction of the GRB. That's the idea, okay? And that's more or less it. GTM Milestone. We started more or less at the same time with every chance project, but we are more fortunate to have more time because the launch date is about 1 year later. So we have more time to work out these things. And we have done our mission design review and system, mission definition review and system design review last year. And tomorrow, by the schedule, but actually it will be this Friday, we will have PDR, that is preliminary design review. And later, at the end of this year, we will deliver an instrument simulation device to NSPO. And next year, 1 year later, we will have critical design review. And then next year, we will be quite busy. We will do some environmental tests, I mean, along this way. And we will deliver our payload, this payload acceptance review. We will deliver our payload to NSPO in May 2023. And then there will be a science mission readiness review at the end of 2023. And we hope this launch will not be delayed for too long. Okay, so this is the milestone. And we are in a good shape. And this is the current GTM team members. We have a lot of young faces. Okay, and hopefully we can see a lot of GRBs. Thank you very much.
Thank you. Thank you, Professor Chang. So are there any questions from the audience? I see Alex, Dimitri online. Are you online, Alex?
Oh, yes, I am.
Alfred.
Yes, I am.
Okay, good to see you. Maybe you can ask a question later. Now, Alfred said he has a question, so let Alfred go first.
I have a question to Professor Chang.
Yes.
Because your sensor is exposed to the ambient environment directly. That means it looks like you didn't have a cover on the system.
We do have, yeah, that module. There is a 1 millimeter aluminum. That box, you see that? For example, this will be made of aluminum. So this is covered. This is covered.
So your simulator is not exposed to outside directly?
No.
Okay. But how about the 1 millimeter thick aluminum will affect it to your detection efficiency?
Oh, the simulation earlier I mentioned actually is with this aluminum. That 1 millimeter aluminum actually is quite good to shield out low energy background. Without that 1 millimeter aluminum, there will be a lot of low energy events. So that's actually a good thing.
Okay, thank you.
Yep.
Okay, Alex, do you have any question on the gamma ray?
Yes. As I understand, you are going to install this instrument to the big body satellite. Yes.
Yes. Yes. That's right. Yes. Like this. Yes.
And this is very important because the heavy satellite will produce, as Chang mentioned right now, will produce very strong background noise of gamma quanta. Yes, and secondary particles.
Mm-hmm.
Yeah. And the problem of shielding, accurate shielding of the sensors, should be considered very seriously. Yeah. Otherwise, the instrument should be remoted from the big body satellite. So did you make any estimation of the gamma ray background based on the platform which you are going to use?
Yes, we did. We did. For example, in our simulation, this effective area simulation, actually scattered light or secondary particles produced by this kind of passive material, not only the bus, but also passive material in our own GTM modules are all taken into account. Okay, so
yeah, I understand you check your instrument, but how about the whole satellites, whole body, passive material of whole satellite?
Yes, the whole bus. We have the mass model for the whole bus, including some internal structure of the bus. Mm-hmm. Yes, we do have that. Yeah.
Okay.
Yes, but what we can do is simulation, right? Okay. So still, the result here I show you this part. These are kind of our version 1 because in the simulation the accuracy here for this version is not yet very good. So we are now starting to have version 2 effective area simulation, which requires more CPU times, yeah, and a more reliable mass model of the whole system, bus and our module.
Okay.
We are now doing that. Yeah.
And concerning to this second version model, I expect you will launch your flight. Your orbit will be near Earth orbit, yeah? Your satellite.
Yes,
that's Earth orbit.
Sun-synchronous orbit, yes.
Sun-synchronous. Sun-synchronous, yeah. It is
kind of polar orbit.
High latitude is polar orbit, yeah.
It's 561 kilometers.
It's okay. Yes, I understand. Yeah. And in this case, you have to take into account also activity of outer radiation belt, because most of such kind of missions, they are launched to the low inclined orbit, say below, say 30 degrees. Yeah, high latitude orbits, they are very contaminated by precipitations. So how do you take into account these effects?
That's true. That's true. That's definitely true. And the orbit, which they call LEO, that's low Earth orbit. But anyway, indeed, SAA and also some regions close to the poles, the both poles, are not good. I mean, particle backgrounds will be very strong. So in our simulation here, we do not consider those regions. And in fact, in the operation, very likely we will also turn off our payload when the satellite enters those kind of region. Okay, yeah. So if the particle background is that high, I don't think we can have good detection. Anyway,
sure.
Yeah.
Well, thank you very much.
You're welcome.
Okay, thank you for very good questions. Professor Chang, I also wondering that how about the ground campaign? Do you have a like an international collaboration or your own campaign plan? Yes.
Yeah, of course. Now for GRB monitor, there are different missions, and people actually are all well connected. So, like I received all the this kind of GCN that's circular anyway. Yeah, and the good thing is that we may also use the time difference of the arrival time at the different missions, different instruments to infer the direction. So in this regard, particularly, we will collaborate with other missions, like from GTM and Corners Wind, or even Swift, and sometimes Integral also detect that. So indeed, this is a very international effort, and I'm in some network of this.
Excellent, excellent, very well. Any other questions?
Yes, I would have one for HK. Hello, HK. This is Christian Fuchs speaking. I wonder, what you just described about you have to turn off your instrument because you get too much background radiation or just in general too many excited particles in certain regions of the magnetic belts. What about the rest of your instrument? Is that then all built from cost parts and you just turn it off to save from, let's call it, incorrect operation?
The rest, you mean?
So essentially the parts of the electronics of your detector that are not just the detector itself, but essentially data readout and things like that. I wonder if that is then designed in a, let's call it, robust way, or, I mean, traditionally people call it radiation hardened, but I'm pretty certain you're not doing any such thing, right? So I wonder how that looks like a bit.
That's good. So that's a good point. But okay, when we turn off, I mean, the whole GTM is turned off, and the issue you raised actually is the radiation damage. And for all the parts and material we use, actually we will do some beam test, and also we have, I mean, from other literature, we know what kind of material, I mean, what is the tolerance of dose. So this issue is taken care. For example, GAGG, this kind of scintillator will be okay. I mean, based on some reference I saw, I think under a beam test of 50 K rad, I think the scintillator still behave very well. So that's one information that we are happy with. And also, we also check the ASIC, for example, the ASIC we use, and that one, we also have some test report about this kind of radiation damage. So we take care of this issue by considering all the different material and all the parts that we use. And the expected lifetime is, say, the nominal one should be, say, 2 years or 3 years. And we will consider the radiation tolerance based on this kind of requirements.
Okay, cool. Thank you very much. So essentially part selection and testing and a bit of well, same choice of materials. Thank you very much.
Yeah, thank you.
Okay, any more questions? Okay, I guess then it's a very good talk and a very good discussions. So if there's no any further question, we have very good talks this morning and very good discussions. So I guess we'll be jumping from the Formosa A to Formosa 7, starting from 1 p.m. So thank you again for joining, and thanks all the speakers to present their very good up-to-date results. So so for people who are interested in listen to the Formosa 7 Cosmic 2 progress, please come back at 2 p.m. Thank you. Please come back by 2 p.m.